Electrostatics Part 3. In previous session we learned about the charged sheet and electric field due to charged sheet and parallel plates, equal and unequal amount of charges. Here the opposite charges are placed, the charge density sigma 1 and sigma 2 on these two plates. Left side plate has the plus sigma and right side plate has the minus sigma. Then these two parallel charged infinity plates divide the region into three. So this is the region 1, region 2, region 3. Here the positive plate exerts field towards left as well as towards right because it emits the field or field lines emitted normal to the surface and exerted to up to infinity. But the electric field intensity is inversely proportional to square of the distance. So the electric field intensity goes on decreases. Whereas in case of negative plate, the electric field is towards the negative charge. Means it is attractive and this is emittive. So this is the basic difference. So the regions, when we are taking about the region 1, region 2, region 3, here the electric field is 0. Why the electric field is 0? Why the electric field is here 0? Because plus sigma minus sigma equal amount of charges. If the separation between the plates are not too larger, then we can calculate the electric field at the three regions. In the case of E is equal to E1 bar minus E2 bar because their directions are opposite. So the resultant is gives us 0. Whereas in the region 2 we are having E1 bar plus E2 bar, both are towards the left direction, means minus of course. So then sigma 1 minus of minus, minus sigma 2, that is nothing but minus sigma. Again you get simply the field here is sigma 1 plus sigma 2 by 2 epsilon naught sigma by epsilon naught. Whereas in the region 3 again once again 0. Each plate contributes 1 by 2 times sigma by epsilon naught. So that is the reason the field here left side 0, right side 0 of the parallel plates only exist in between how much, that is sigma by epsilon naught. Sigma by that is epsilon naught. So this is what exactly we are using in latter case parallel plate capacitors. The electric field existing between the two parallel plate capacitors is sigma by epsilon naught. Now electric field intensity due to uniform charged thin spherical shell. So consider at a point P, suppose here outside the charged shell, this is the center and the radius R, hollow one, and here the total charge is Q, charge density is sigma. Once again we are considering a point P. Here assume a spherical Gaussian surface which is passing through point P. Then we are going to calculate the electric field at the point distance R. Consider small Gaussian surface ds bar, area vector is normally outward, electric field also in the same direction, radial direction. So these two are making 0, means area vector and electric field at this point P is making 0 angle. So from Gauss law, the total flux is a closed integral E bar dot ds bar, which is equivalent to 1 by epsilon times the charge enclosed. So this entire Gaussian surface here, this entire Gaussian surface, what is it is enclosing? The total charge inside, the total charge inside. So the total charge here is Q. The total charge here is Q. So here Q by epsilon naught. So what is the value of E bar dot ds bar? Integral E bar dot ds bar, E bar along this circumference or along this spherical surface of Gaussian is remains same because it obey inverse square law. The radius of the sphere is constant, so according to inverse square law, E is constant for the given amount of charge, only integral ds, because cos theta already we discussed that theta is here 0, cos 0 is equal to 1. So now this value, when we are doing this calculation part, what we are getting, integral over closed integral over surface area, that is nothing but 4 pi r square. So E is equal to 4 pi r square. So we require E. So E is equal to 1 by 4 pi epsilon naught q by r square. This is just like a point source. Means the field existed by electrostatic field intensity due to uniform charged thin spherical shell behaves like the entire charge G is concentrated at its center, and it is equivalent to the same expression what we learned in previous case. At point A, on the surface of the shell, we will see here, simply we are considering the Gaussian surface once again on the surface, and we are taking the same measurements and calculations, but in the previous case the point P is outside, now the point is lies on the surface. This is the only difference we get. By using the usual method, we get the expression E is equal to q by 4 pi epsilon naught into 1 by r square. This one now at a point B inside the shell. So this is we have seen outside on the surface. Now the point B, assume a Gaussian surface which is passing through this point B. This is, of course, the charge is lying outside. So how much charge is enclosed by this one? This shell Gaussian surface does not enclose any charge, not at all. So the Gauss theorem, when we are talking about the Gauss theorem,